So hello everyone, thank you very much for the introduction. I'm Giovanni Camurati. Welcome to our recent work on Noise-SDR, which is a method to modulate electromagnetic leakage in an arbitrary way using only unprivileged software. So first, a bit of context. Electronic devices produce a wide range of emissions, physical signals, including, for example, electromagnetic waves. And this leakage, these signals, are somehow related to what the device is processing. So they can be used to compromise security. For example, side-channel attacks break cryptographic keys. And tempest attacks recover plaintext information, for example, a video on a screen. In addition, an attacker can try to build a covert channel by modulating actively this leakage, trying to transmit data, in an attack that is called soft tempest. Soft tempest is usually targeting air-gapped devices, which are completely disconnected from the network. So the threat model is that even if the attacker has the ability to run code, this attacker cannot exfiltrate data. But if there is leakage, and if the attacker can modulate this leakage to encode information, well, then communication becomes possible again. A classic example of soft tempest is Tempest for ELIZA. So here you can see my screen. I'm playing a YouTube video with some stripes. And on the right-hand side, you can see what I observe on the radio spectrum with the radio receiver. And what we can observe is that depending on the frequency of the stripes, we have different frequency components on the radio spectrum. And if we interpret them as tunes and we listen, we play audio, we can hear Beethoven's Fürelise. However, in the real world, we want to transmit binary data. So after having identified a carrier, we might want to turn it on and off in order to encode ones and zeros. This is called on-off keying. And we can also do the same by changing the frequency shift keying. These are two simple types of modulation that can be implemented with this loop by previous work. So the idea is that there is an operation that can trigger the emission of leakage at a certain frequency, F leakage. And if we repeat this operation over and over in a loop, half of the period on, half of the period off, then what we can do is to basically cross-modulate a square wave on top of the natural leakage. If the attacker turns this on and on, well, then we have on-off keying. But we can also change the period of the loop, and then we can implement frequency shift keying, which can be binary, or there could be multiple values, or even you could approximate a chirp or more complex signals. There is a wide range of papers exploring many different types of leakage, different physical principles. We focus on electromagnetic radiation. And in general, previous work uses simple custom protocols and simple modulation schemes. And generally, it targets exfiltration in the context of air-gapped devices. The problem is that with this, you generally need custom receivers. And there, you cannot implement higher-level protocols and error correction and pulse shaping or more complex features of the radio transmissions. And these are also fixed implementations with a single application. In the meanwhile, real-world radios are generally software-defined. That is, the signals are completely created in software, and then there is a minimal set of hardware components that you use to turn them into actual physical waves. They can shape any signal in an arbitrary way. They can achieve high performance at the physical layer, but also implement complex protocols even at the upper layers, and they can virtually target any application. So the question becomes, can we do more with soft tempest? Can we make it more similar to a software-defined radio for what is possible? More precisely, this requires trying to modulate the electromagnetic leakage in an arbitrary way, changing its amplitude, frequency, and phase, and doing that in a software-defined way so that we can be flexible, achieve high performance at the physical layer, and explore more applications. There is a big challenge to answer this question, and that is we have a very limited primitive. We can only basically turn the leakage on and off. We can access DRAM and create a leakage at 400 megahertz or not. And on the other hand, what we want to do is generate this arbitrary sine wave at a certain frequency with the amplitude and phase that we desire. The solution to this problem is passband 1-bit coding, and in particular, radio frequency PWM. This is a very fascinating mathematical topic. In short, we want to generate a generic sine wave modulated, and we approximate this with a square wave. Let me illustrate this with an example. So the signal in orange is the signal that we want to transmit. It corresponds to a digital protocol with 3 subcarriers, each modulated in binary phase shift keying. And we approximate it with the square wave in blue that you can see on the top. If we go to look at these 2 signals in the frequency domain and we focus on the carrier frequency around the band of interest occupied by this protocol, we see that the 2 signals are basically the same. The blue one is a very good approximation. All the errors, all the noise is actually spread out of band where the receiver will not look for any signal. So based on this idea, we implemented the Noise-SDR to achieve arbitrary modulation of electromagnetic leakage. We decided to demonstrate it with DRAM. So if we access DRAM, we generate a leakage at F leakage, otherwise we don't. And we have our data that we want to transmit. In a first step, we implemented the upper layers and the physical layer using a generic existing software-defined radio tools. Of course, it can also be custom. And what we get from this is the samples, the baseband samples, amplitude and phase, or for those of you who are familiar with software-defined radios, the IQ samples that we would normally send to a hardware dongle like a USRP or a HackerF to turn them into physical waves. But we don't have it. So what we do instead is to apply radio frequency PWM. So we modulate them on top of a square wave at an intermediate frequency FIF of our choice. And this is still all in software. Then the square wave is basically telling us on, off, right? So we can use that to access DRAM or not. And this has 2 functions. First, it creates a natural physical signal. And second, since the leakage is at F leakage, it brings our signal to radio frequency at carrier frequency F leakage plus FIF. If the receiver tunes at this frequency, it will receive a cosine wave with the amplitude and phase of our choice. So how do we implement this in practice? So it's very simple, actually. We just, in software, generate a cosine wave with the frequency and phase that we want. Then intuitively, the square wave should have the same periods. So by looking at the 0 crossings, we find out the periods of the square wave. And then we apply a small pre-distortion on the pulse width to control the amplitude of the final signal. We are left with a list of timings that we use to control the accesses to DRAM. At the first sight, this loop looks like previous work, but the key difference is the way in which we control the timings with radio frequency PWM. And intuitively, the entire signal is now defined by a square wave, by its timings, so timing accuracy is very fundamental to control the bandwidth and the quantization levels. For this, we need a leakage that, besides being leaky, it's also fast, and we need an accurate, stable clock. For the clock, we use clock get time, though there are many other primitives available in literature. And for the leakage, there are many types. In the paper, we focus on DRAM accesses. Here, I want to show you an example on V8, ARM V8. So inspired by Rowhammer, we first load a memory address, and then we use an unprivileged cache instruction to invalidate the address so that we can always load from main memory and create a leakage. We have integrated Noise-SDR with popular radio tools. For example, FLDG, which is an amateur radio tool implementing a lot of digital protocols. So basically, you can just give the data that you want to send, the mode, and the intermediate frequency, and it will start producing physical waves that on the other end of the communication, you can just receive with a normal radio setup with a software-defined radio and FLDG running on a laptop, for example. We also integrated Noise-SDR with GNU Radio, so there you generate first an IQ file, then you convert it to RFPWM, you have a file of timings, just a text file, and you can give it to the Noise-SDR loop to turn it into radio waves. We have evaluated Noise-SDR in many scenarios. Basically, the software-defined approach gives us a lot of flexibility in trying a lot of protocols, architectures, and devices. You can see a few pics here. Then you can also look at our GitHub for more videos and demos. However, Noise-SDR also comes with a few limitations. First of all, like any soft tempest attack, there must be a leakage that we can control, so this is device dependent. And then we have a limited bandwidth, a few megahertz on ARM-V8 as a maximum because of the timing resolution that we can get, and also a limited choice of the carrier frequency because we can choose the intermediate frequency, but we are still limited by the harmonics available on the device. For example, the clock of the DRAM. Noise-SDR has a security impact on 3 main threat models. So the first one is classic exfiltration, where the attacker takes the victim's data and exfiltrates them to another attacker-controlled device nearby. But then we also have tracking, which is a bit similar, but the idea is that the data are now controlled by the attacker. It's a tracking beacon. So here it's very useful to use, for example, offline Noise-SDR, because a very tiny piece of code can create a quite complex signal shape and a quite interesting beacon. And then we have also explored the idea of injecting malicious data from the attacker to another receiver nearby, which is now a victim. Here are a few examples of exfiltration. The key message is that we can either go long range with a robust but slow communication, or go at a bit shorter range and achieve very fast communication. It's very easy. We just use FLDG basically and choose the right mode for the right device, for the right situation, for the goal that we want, without much knowledge, skills, or implementation efforts required. Here you can also see that for reception we have an SDR dongle and a smartphone with FLDG running on it. This is an example of tracking on a smartphone using a protocol which has beacons that can be easily received at even below the noise floor. And finally, an example of injection in which we are at a few meters from this handheld radio. We first enable it, then inject audio, human voice, and then we disable it again. To defend against Noise-SDR, we might want to reduce the leakage in hardware, but that's hard. Or reduce the timing resolution that software has, or application-specific countermeasures. For future work, we would like to optimize the implementation, try other leakages, other languages, because the principle is general, the implementation is an example. And we would like also to find more examples of injection in radios, in sensors, maybe even radios and sensors on the same device, exploiting radio frequency interference on modern devices. So to conclude, Noise-SDR has achieved arbitrary modulation using passband 1-bit coding, and DRAM access is an example. It's flexible and performant, though there are some limitations on bandwidth and frequency, and we have implemented it on many architectures, and we have shown many security applications. Noise-SDR is open source. Feel free to try it out, and I'm now here available for any questions you might have. Thank you.
Let's thank our speaker. Hi. Questions, please head up to the microphone, and please let the speaker know who you are and where you're from while we're waiting for the first person. Giovanni, very nice talk. Just a quick question for you. I really appreciate you talking about the limitations in the work. Can you talk a little bit about who you see the adversary is here? As in, these are really cool techniques. Someone is trying to intentionally remove the air gap, or are you looking at ways in which something already on the machine could do it without additional assistance?
Sorry, for the very last part?
So is your adversary intentionally plugging in extra things to intentionally bridge the traditional air gaps? Is it software running that's trying to take advantage of extra interfaces? What's the practicality of the attack now, and what steps do you see needing to be put into place ultimately to achieve it in real life?
Oh, yes. Okay, so I think the key point in the threat model is that we're considering a piece of software that should not have access to any communication interface, and we give it a communication interface. And then what we are doing, this is classics of Tempest, but what we are doing is to making it easier. So for me, the practicality of, all the limitations in terms of difficulty of placing the software on the device or having a leakage there are similar to classics of Tempest, but where we help with practicality is that it becomes very easy now to transmit. And all the techniques like error correction and interleaving, they really make everything more robust and achieve better performance.
Yeah, I liked your final slides showing potentially taking advantage of other pieces of hardware. But let's go to our microphone. Eric?
Hi, Eric Pauly, Penn State. So you mentioned that you got around 8 megahertz bandwidth through this technique on your example. In terms of after error correction, what was the resulting bit rate that you got out of that?
Sorry, I didn't hear the last part of the question.
So you'd mentioned your bandwidth in terms of megahertz. After error correction and all of the encoding, what sort of bit rate did you get as a result of that?
Oh, okay. So basically, the best we get was this few megahertz where we managed to transmit GLONASS, CA codes, which are like 500 kilohertz, I think. But for data transmission, I have it here. Basically, when we use fast short range with 3 PSK, we achieved something like 600 words per minute. So that means a DSA key in a few seconds.
Great, thanks.
Let's thank our speaker one more time. Thank you very much, Giovanni.
Thank you.